I asked everyone to implement string.h from scratch, as much of string.h as they could from scratch. So yesterday we went over the string.h library. For those of you who weren't here, I can briefly talk about what we did. So effectively, the only things that we actually cared about were string cat, strchr finds the first character, string comp compares strings. Let's see, string copy, you copy one string into another string, all the straightforward ones. And strlen, which computes the length of the string, right? So I asked for homework last night for everyone to implement as much of string.h as they felt comfortable implementing. So this is Dan Yee's solutions. So overall, Dan's solutions were pretty good. I thought that he did a good job. First one right here is string length. Pretty straightforward. You pass in the string, and then you literally just check every single character, and if it's the null character, you stop and then return the length, right? So while string at the current position, which he has as length, is, and you're incrementing this each time. And yeah, so while the character isn't the null character, then you return the length. Good. Okay. Next up is string compare. All right, so let's see how you're doing the string compare here. So this should return 0 if they're the same and -1 if they're not the same in lexicographic order. This looks right. So effectively you get this max length, then you do a for loop up to the max length. I think the issue, I think you want min length here rather than max length, because what happens when you hit the null character? Does the null character get counted as first lexicographically? I think that, so for string comp here, you want to go up to min length, and then I actually don't know how they would implement this, but I'm fairly certain you would get the min length of the string, and then if it's less than, it would be in lexicographic order. So yeah, okay. This actually might work. I'd have to test this. This is, I actually don't know how string comp works behind the scenes, but for most cases, this looks like it would work pretty well. Okay. String copy is literally just setting the individual characters of the string in the destination to the from the source. So effectively, we pass in the destination and we set the first character to the first character here, second character to the second character. This is exactly what we want. Just a for loop that copies character by character from the source into the destination. Very good. String dupe copies the string, so it basically just mallocs and then string copies, and that's exactly what we see that Dan does here, is a malloc and a string copy. Very good. Okay. Now for string concat, this is what Dan has done wrong. He has, this one is, you can't malloc in string concat. All you're doing is basically, I can actually delete this here, so I'll write in my solution for string concat. Effectively, what you're doing in string concat, this should be an immediate giveaway, is the fact that this is const char and this is char. The fact that this is const char means that we're not going to modify the second parameter, but we are going to modify the characters that this pointer is pointing to. So effectively, all we have to do here is basically say, okay, I'm going to, well, we need our index first, so we need to get the length of string 1 first. So int len str1, and that's going to be string length of string 1. That is not the right thing. Okay, there we go. And then all we're doing is copying in up to the length of string 2 into string 1. So string 1 of len of string 1 plus I is string 2 sub I, and I believe we are returning string 1 because that is the concatenated version. This might not, I forget if string, I don't think string length counts the null character at the end. It doesn't, right? I'm not crazy here. You're not counting it in here, right?
Oh, I'm not.
I'm fairly certain it doesn't count the null character. So effectively, string length length str1 here is the length of our first string, right? And then we're just appending onto the end of this string, effectively, the characters from string 2. There's no malloc going on or anything. It's relatively straightforward here. Okay. So that's some of the ones that I asked for. I think some of the other ones I asked for, str for the substring, and then spn is probably the hardest one. So, I mean, if you guys ever want to implement these, this is fun. We can do, you can spend a lot of time implementing string.h functions. It's definitely a great exercise to really master the string library. Okay. So today we're planning on, does anyone have any questions about the string.h homework, by the way, before we move on? No? Anything about strings? Any questions about strings? Otherwise, we're going to move on to enums and unions, which are terrifying and kind of cringe TBH, but it's all good. All right, so you can type in workshop if you have any questions as well, and I'll try and answer them in there. But for now, we're going to move on to enums and unions. So enums and unions are pretty straightforward. The first thing that we're going to talk about is, I guess, enums. Enums are the easier of the two. So effectively, let's get our main function out here. Return 0. All enums are is us essentially defining a type that can have one of a few different values. So I'm going to declare enum color as, that is not how you do it, and I don't know why I wanted all caps. Normally you have enums be capitalized, just like you would have a struct name be camel case capital, or not even camel case, just capitalized. And we're gonna put some stuff in here. So red, blue, pink. Okay. So effectively, this should actually work, right? Yes. Okay. Very good. So what this effectively means is we've defined our new type that can only take on these values. So I can effectively say now in my program, I can declare a variable of type enum color, and I'll call this my color. Okay. So the same way an int could take on a number, our enum color can only take on one of these three values. So now I can say my color equals red. I could say my color equals blue. I could say my color equals pink. But what's actually happening behind the scenes here is that red, blue, and pink are effectively just names for numbers, is what's actually going on here. So the enum is actually a numeric type that stores, that's why it's called an enum. It stands for enumerate. So effectively, we're enumerating all of the possible types as, can you type def enums like nums, like enums? Yes, you can. So I'll show an example of that next. But effectively, what's actually going on here is that red is the number 0, blue is treated as the number 1, and pink is treated as the number 2. And you can actually see this if you printf an enum value. So if I do printf and then %d, that is a $sign, not a %sign. I need to turn the light on in my room so I can actually see my keyboard. All right, there we go. %d, and then we actually print out something like red. So if I actually print out red, we're going to see, I'm gonna add a new compiler here, get rid of, no, not compiler, execution only, there we go. So we can see that red is actually printed out as 0. If I try printing out blue, we see that it prints out 1, and if I print out pink, we see that it prints out 2. So the reason that this is very useful is because this allows us, there's a lot of instances where we want numbers to represent something, right? So colors, for example, are a really good example of this, where we might not necessarily want to represent colors as the way that colors are normally represented with all of their fancy RGB values. We might literally just want a color to be represented, say, back in the old days of MS-DOS, where there were only 16 possible colors, you would want to have an enum for each of those 16 possible colors. to use rather than passing in the number that identifies what color you're using. You want to actually have a string that refers to that so you know what it is, right? And another popular use for enums is going to be error codes. That's like the number one use of enums that we're going to see. So Max asked if you can type def enums the same way you can type def structs. And yes, you can. I can very easily change this to type def enum color and then color. And now I can declare my enum color with the enum out front, or I can remove the enum in this definition. And now I'm just saying color, color, and effectively the type of my color is going to be color, and because it's an enum, it means it can take on one of these three values, which again, it's just numeric. So if I say my color equals pink, and then I try printing out my color, we can see that my color is 2. So another interesting thing that we can do is actually check how big this is. If I do something like the size of operator on color, we can see that it's actually probably only going to, okay, so they're representing color as an int. They're making color take up 4 bytes of space, which is actually a huge waste because we only need 3 we only really need 2 bits to represent this. So it would, I wonder if we optimize this. If I do O3, if they're going to see this and optimize that down to 1 byte. No, they don't. Okay. So I guess they're literally having enums in C be represented as ints. So effectively what this is secretly saying behind the scenes every time that means is it's effectively the same thing as you saying up here. So this would basically be along the lines of me saying hashtag define color int, hashtag define red 0, hashtag define blue as 1, and pink as 2. Define. So effectively, I can get, if I get rid of this, this should do the exact same thing. Oh, I'm not actually printfing anything here. My color. So this is almost exactly equivalent to this enum right here. This is doing it with defines, and this is doing it with the actual enum here. So these are equivalent. But we like to use enums instead because obviously they're easier to read, and you can do stuff like, I mean, you can do size of on color in this as well. I think I spelled color wrong every single time. COLOR. Is that how you spell color? I actually don't know. Time to Google search if I spell color right. I don't. Is that how you spell color? Why am I so? Why is this? This is terrible. All right. All right. Well, you know what? If Dawn says I'm spelling color right, I'm spelling color right. Okay, we're set. Okay, what are they? Oh, they're whining because that's I'm doing the type def with this. But effectively, this is the defined version and this is the enum version. They're identical. So what we actually care about now is how can we use enums? What are the best ways to use enums? And my answer to this is that effectively, colors you'll see, but there's a lot of situations in your program where you want to pass some kind of state as a number, but you don't want to actually have to remember what the number is. So settings, for example, settings that can take a few different particular values. You don't want to pass the string and then check against the string every time. It's way more efficient to pass a number and check against a number every time. But there are instances, especially error codes, where you might want a string that actually represents this thing, right? So a lot of the time you're going to have, especially libraries, are going to have an enum lookup table where you pass the enum and it's going to function as an index into a array of strings. And with that, you're going to be able to actually look up and get what the enum type is. In fact, I think the homework tonight, what I'm going to have you do for homework is write a define macro that generates an enum and a lookup table for the enum just by passing in the names of each of the things. So that should be fun. I'll write that down later. I haven't actually written that up yet, but that's going to be a fun assignment. Maybe I'll talk about Vargs today so we can actually do that because Vargs are a lot of fun. We haven't talked about Vargs yet. I love Vargs. Okay. So on top of colors, we're going to talk about how to actually use enums. So one the match made in heaven is enums and switch statements. Enums and switch statements are perfect for each other. So say you have a function that's taking in some enum, right? So I'm going to have a function called f, let's call it, what do I want to do here? I'll have it be a void function that prints things out with fancy colors. So I'm going to actually, do I actually want to do it, have it print out in a special color? Because we can easily make that happen. I can make this happen. All right, I'll do something where I want to do a colored version of printf. So I pass it an enum with the color that I want to printf with. And yeah, okay, so this will be fun. Colored printf. And the first thing I'm going to pass in is, I'm not going to call it colored printf. I'm going to have it be colored print. You're going to pass in a const char pointer of the string that, you know what? I won't have it be const. I'll have you pass in a char pointer to a null terminated string, str. This is the string you want to print out. And then your other parameter is going to be the color of, and obviously it can be one of these three colors that you actually want it to print out. So color, and I'll have the color name BC. So the match here is, what we obviously want to use is the switch statement. Switch statements and enums, again, match made in heaven here. We check based on the C, and then all of our cases are going to be the enum names. So case, in the event that the color is red, we do something. In the event that the color is blue, we do something else. In the event that the color is pink, we do something else. And you'll oftentimes see enums that have a default value called like null or something, like none. And in that case, we're going to have both a none, and you can easily hack an enum since it's an int. So we're also going to have the default case. We're going to have the none case and the default case be the same thing. Default, I can't spell that. D-E-F-A-U-L-T. There we go. And I'll have it do something down there, and I'll throw all of these breaks in. Break, 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 and no break on the default because it just exits immediately. All right, so now to actually have it do the printing, we are going to see if Godbolt terminals allow us to use Ascii escape codes. So I don't know how many of you know about this, but there's actually, oh, it's ANSI escape codes. There is actually escape codes that let you color your terminal text. Here it is. Okay, so I'm going to be using, let's see, what do I want to use here? Should I use, I could use, all right, I wanted a pink. This isn't really pink, but I'll use this, sure, why not? So in the event of pink, we're going to do printf, and obviously we're %s'ing this string, but we're also going to be actually doing the color coding. So I'm going to use \e, and are they, let's see. The real question is if they let you color code the Godbolt terminals, which I have a sneaking suspicion they are not going to let me color code the Godbolt terminals here, but we're going to make an attempt. We are going to make a decent attempt here. Let's see. 131. So 1 semicolon, and then the color of magenta is 95. No, where am I? Here we are. 95, and after that, we're going to escape into 0M. And I forgot the M here to end that. And effectively, this should print out our str with whatever color we've just provided here. So now I'm just going to test to see if we're allowed to do colored printing by putting all of these here. And by default, we're not going to color anything. So I'm going to get rid of all of these color modifiers here. Don't worry about the color modifiers. Just know that this is possible. It's kind of fun to mess around with the color modifiers, especially if you're doing like a text-based RPG. Okay, so down here, I'm going to do print, not print. What I name this function? Color print, colored print, colored print, and we're going to print in red, or well, the only thing I actually have implemented is pink, and we're going to print hello. And let's see if this works. I have a sinking feeling it won't, but we're going to see. What are they yelling at me for? Passing argument 1 of color print makes point. Oh, I switched the argument order. There we go. Oh yeah, look at that. So now I'm printing out a pink hello, hello pink exclamation mark. So now I can implement the other cases. So let's go look at the other colors. Think I have a blue. So that's 94. I'm just going to steal this 94 really quick. Bright blue. So in the blue, I'm going to replace this 95 with a 94. What else did I have? I had a red. I'm going to take 31 for my red. Actually, I'll do 91 for bright red. Let's see, 91 on my red, and that's everything. So now I can change between pink, blue should make me print out a blue hello, and red should make me print out a red hello. So isn't that fun? This is a nice example of where you would actually use enums. We are basically passing some set value here, which is going to be an integer. And then in the event that this is none, we're not going to do any coloring. And our final thing is we pass some weird value that isn't actually an enum. It's going to default to this. So we can see here that I'm actually passing a 56 into this color C right here and it's able to handle that, but it doesn't actually have any types assigned to this, so it doesn't know really what to make of this. It's not assigned to a real enum. So in the event that someone does something screwy like this, we have this default case implemented as well. So in the event, default and none are going to be so if you pass some weird thing, it's going to go for the default case instead. So this is effectively how, I mean, you could also do something like this and then throw an error right here and say printf non-valid color, something like this. And now it yells at you when you do something like that instead of a default thing, instead of one of the actually accepted enums, right? So this is a neat example of where you could use enums. Again, it's always going to be better to use a switch statement for your enums rather than an if-else chain, because if-else chains cannot be implemented as lookup. Well, some compilers would implement an if-else chain like this as a lookup table because they're smart enough to do that nowadays, but it's still always going to be better practice to use a switch statement here for handling your enums. Okay, so the other thing is you might have an error handler where you're passing in. So for example, I think the best example of this would to actually be to show off a C library that uses enums for its errors. So what I'm going to look at is the Vulkan errors. Okay, VK result. So VK result is an enum that is defined to have all of these different error codes as various numbers. So they actually show us here in the documentation what's here. So another thing that you can do with enums is you can literally set the number that your enum represents, but normally it's good practice to let them decide what the enum is, have the compiler decide it. But there are events. So for example, I could literally assign the enum whatever of these colors I wanted, and then literally use the enum inside of my thing here. So if I did something like this, which this is a terrible idea, but let's say I wanted to actually, so back to the color example, I could have none not be anything. I could have red equal 91. I could have blue equal 94 because that's what I'm using as the blue color right here in the terminal color codes. And I could have pink equal 95. And effectively what I can do now is instead of having this enum statement at all, what I can actually do is go down to not enum statement, the switch statement. I can get rid of this entire switch statement and do something like this instead, where I print f and then I put the enum here as %d, and then I do c comma str. And now if I do red, we're going to see that this ends up as red hello, and then blue, pink. So for stuff like this, where the number actually has some direct meaning, you can very easily do something like this, where you can assign a special number to your enum value. As to why you would want to do this, this is probably one of the few cases. We can see that Vulkan does some fancy stuff where they're like, oh, we're going to assign some random number here. Sometimes these could also represent various flags, but we're not going to get into that. They're basically saying, all right, yeah, we're going to have our enum represent, every bit is going to represent a different flag of something that represents something, blah blah blah. We don't really care about that. All we really care about is being able to say, okay, I want my pink color. I don't want to type out 95 and pass in 95 because, again, programs, every good program is a human readable program, right? You want to be able to read your program as a human and have someone who's never seen your program before actually understand what this means. If someone sees colored print hello 95, they're like, what the hell does 95 mean? But if they see colored print hello pink, they don't even have to look at what colored print does to say, okay, I can guess that this prints out hello with the color pink, right? So that's, again, enums really help towards the readability, right? And no matter how you're implementing the enum behind the scenes, what really matters is someone who's coming to your code for the first time and sees this function that takes hello and pink can pretty easily guess what's going on here, right? Okay, so back to actual error codes, though, which is what I wanted to talk about. This is a big Vulkan enum. So effectively, VK result is an error code from some Vulkan function. So the way that Vulkan implements its functions, and for those of you who don't know, Vulkan is probably the fastest graphics library right now. So it's basically an interface to your GPU. So all the fast video games use Vulkan as their underlying graphics API. But what we care about right now isn't actually really what any of this necessarily means, but I am going to briefly just move this in here so we can talk about error codes. So effectively, what we have here is a bunch of different codes from functions that tell us how the function failed, or if it didn't fail, we get VK success returned. So effectively, what's actually going on here is there's going to be some Vulkan function that does something, and it's going to return some VK result. So we have VK result, some function, some func, and this is going to take some blah blah blah. We don't really care what it's taking. We don't even have to say it takes anything. But basically, long story short, what they're doing is their functions are probably thousands upon hundreds of thousands of lines long. I'm absolutely sure somewhere in the Vulkan driver they have functions that are hundreds of thousands of lines long with gazillions of conditions. So effectively, what they're doing is they're saying, all right, if my function fails in this way based on something when I'm communicating with the GPU, blah, 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 I'm going to return this error code that says that we failed this way, blah, 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 blah. And then you, as the user, can actually check to see how you failed down in main, right? And you can have a big switch statement as a user to basically say, well, here's how I want to handle this error, here's how I want to handle this error, blah blah blah. There's a lot of different stuff that you as the user have to handle based on what the error is. So effectively, this is probably the number one use of error codes, is managing handling of different types of errors. In fact, we can see as users that sometimes if we, so for example, I was talking to Tyler about this the other night. You probably know how when we run the program we return 0. So what this actually is, though, these return codes, we can interpret these as enums. So I might do something like this and say int I equals 10 divided by 0, and huzzah huzzah, this is a divide by 0 error. It sends a signal, which does, it's long story short, it's a signal that signals that we've done some illegal math operation, right? And this crashes the program. We can see, despite the fact that we say return 0, here we're saying it says returned 136. Now, as humans, we have no idea what 136 is, because int is supposed to return, main is supposed to return an int, right? But what 136 actually is behind the scenes, they have some big enum that's basically saying, okay, we want to return this code and it's tied to some special meaning. And if this was a sub process, then we would actually be able to process this as an enum and cast it to some enum, which would probably be in, I'm assuming this is Linux. So if we look up Linux program return codes, we're gonna get some fancy thing. Let's see. We'd probably have to like look into the Linux kernel to see what the codes are, but they definitely have a big list. Let's see. C language. Oh, so C defines its own error codes. So exit success is 0, and then exit failure is going to be. Let's see. I want them to give me. I'm sure there's Linux error codes somewhere. Come on. Are there standard exit codes for Linux? Yes, and they're using ones that aren't defined by the C standard already. So in our case, 136 plus n. Fatal error signal n. So this is 128. We're at 136 plus n. So this is a signal error telling us we've divided by 0. Anyway, we don't really have to worry about this. But what effectively all I'm saying is you're able to identify errors and cast them to enums if you're running this in a subprocess, right? So that's the other main use case of enums is error codes. So main uses of enums, colors, error codes, and basically any time that you have some need to represent program state as, or any time that you basically have a list of things that something could possibly be, you want to use an enum. That's always the main use case. And you see this a lot from people who are like, oh yeah, I'm gonna pass an int to the function that represents what the function should do as like, a state. But you should always pass an enum instead of an int to make things human readable. That's always the standard. And enums are implemented as ints behind the scene anyway, as we just saw. So it's not, there's no reason not to implement um, error codes, and anytime you want to pass an int to something to represent state, always pass an enum instead. So that's enums. Any questions about enums before we jump into unions? Unions are a lot of fun. I hate unions, but you know what? We're gonna have a lot of fun with unions. There's really no good real use cases for unions, if I'm being completely honest. But we're gonna take a look at unions and have some fun with unions. Okay. So feel free to ask questions about enums in chat. I'm gonna get started on the union explanation. So unions are special data types that basically let you combine multiple data types into one thing and use the same memory for multiple data types. So we actually have to understand how the memory is working behind the scenes, but before we do that, I'm just going to have some arbitrary union. And to do that, I actually have to think up a good example of why you would ever want to use a union for anything, which, to be completely honest, there's I've never I've used a union unironically once as like a typecast, and that's about it. In embedded system development, you use unions all the time because you want to save as much memory as humanly possible, which is really what unions are for. But the other case is you want to convert between multiple types in one location. So what I'm going to do here is I'm going to actually do. Let's do. Okay, I have a good application. So I'm going to have character data, char data. So effectively what this union is going to be is it is going to let us convert between 50 characters, which is going to be character 50, and let us convert between char. I'm going to give this a name, chars, and it's going to let us convert between. So it's an array of 50 characters and an array of. What, you mad about my emails? I don't delete my emails. I just have a gazillion emails. Okay. Back to. Do I have I have string.h, but I don't need it. What I really want now is hashtag include std int.h. So we haven't gone over std int.h, but std int.h is actually really straightforward. In fact, why don't we go over std int.h just so I can explain what's in std int.h? But let me do where's my CPP reference? The best reference fixed with integer type since C99. All right. So effectively, I love these. Effectively, what this is int is kind of an annoying data type. All of the data types that we use typically are very annoying because they vary from system to system, even though on Windows and Linux they're all set. So you might remember char is 1 byte, short is 2 bytes, int is 4 bytes, and long is 8 bytes, right? So that's normal, right? But on some systems, ints are actually going to be 2 bytes, and longs might be 4 bytes. So effectively, there's no guarantee on the actual lengths of ints and longs on a per system basis. So what stdint provides us with is fixed size numeric types, which are either signed or unsigned. So instead of using char, which we have no idea what it's going to be, we can use uint 8 underscore t, which this is always going to be an unsigned 8-bit type that basically you can store from 0 to 255 in, right? Whereas uint underscore 16t is always going to be 16 bits wide, and you're always guaranteed to be able to store an unsigned 16-bit number in this. And same for this uint 32t. These are, I love fixed width integers. I always use fixed width integers. This is they're the best. Okay, and then same with uint64t, and we can actually see in here they define uint64t down here, 32, 16, and 8. Then there's fast, which this is like if you're really concerned about speed on various systems and cross-platform speed, you use uint fast 8t, blah blah blah, and they have this implemented to be the fastest possible thing on whatever operating system you're on, because typically the C library is implemented by the person who's writing the operating system. So you don't actually have to worry about this. But this is all we need to know: is we have access to these uint types fixed with integer types, right? So always stores 8 bits, always stores 16 bits, always stores 32 bits, always stores 64 bits. And up here is fixed with non-unsigned, so these are signed integer types, and no one ever uses the signed integer types unless you want to store negative numbers, right? So that's the only use case you'd have for this. But normally when you're using UNATs, you're exclusively looking at unsigned, so you would use the uint types. Okay, so next we're going to talk very briefly about what I wanted to do, which is basically say we're going to convert from chars to into ATs, 8 underscore t. So what's actually happening here behind the scenes is we have two different lenses. I don't know what I'm doing here. What's going on? Okay, I want that, and I want this to just be called data. So effectively what this is here is when I declare a char data type right here, effectively what this is doing is this is allocating the largest size possible for what we have inside of this union. But in this case, these are actually basically the same thing. Chars are just signed, UNAT is unsigned. But this is actually represented as numeric, right? So it's interpreted as an integer rather than a char if we're doing addition and stuff, which you could theoretically do with chars too, but it would be signed and it's system dependent. But basically what I'm saying to do here is, okay, so I have a string and I have now an array of, so this would be interpreted as a string. So why not just call this a string? Sure, why not? And then this would actually be the numbers in the string that we're able to get a view in as an array of basically integers, 8-bit wide integers that we're going to be looking at. So I'm going to declare char data, and let's call it data. Why not? And then I'm going to put into this string right here, I'm going to do, should I run strcpy on this? I'm going to have to because it's not constant. strcpy, and I'm going to include string.h here, string.h. And effectively, I'm going to copy into, I shouldn't call this data because it has data. What should I call this? Call this like str convert or something instead. CVRT, string converter. And I'll have this be CVRT. Sure. So I'm going to copy into the string component of this a string. So I'm going to copy in hello world exclamation point. This should work. Are they going to yell at me that I'm not allowed to do this? What are they yelling at me about? The fact that I don't have this and I haven't used the word union here? Well, I typed using. Okay. So effectively what's going on here is I'm storing hello world in the string component of this, but now I actually also have a lens into the data component of this. So if I wanted to print this out character by character, I would be able to actually do this. So how do I actually want to do this? I want to actually get the UN8 data from this. And to do that, I'm going to, why not just do a for loop over it and display each individual Ascii character from the data component? Sure. So I'm actually going to get the length like this using strlen. This is a weird way to write the for loop, I know. Int I equals 0, while I is less than string length, cbrt string, and then I'm going to get a reference to data sub I from cvrt.data. And I'm going to print this, print f. I'm going to need to include this hashtag d. All right, so this should theoretically print out hello world here if I can get this to actually run. And they want me to include stdio.h. I know. Okay. What are we missing? Okay, and let me print each character on a new line. So effectively what's going on here is I now have two lenses into the same data. I think the best way to talk about what's actually going on here is to talk about this in terms of memory by pulling up MS Paint. You guys know I love my MS Paint. So let's actually take this and take a look at what's going on here. Okay, so when this program starts running, the first thing that happens is this union declaration CVRT. The union allocates the amount of memory needed for the largest data type in here. But the thing is, char and UNAT are the same size, so it's always going to allocate 50 bytes of space. And because we're declaring this union inside of main, this is allocated inside of main's stack frame. So we're inside of main stack frame right now, and we are allocating 50 bytes of memory effectively. So this is CVRT. This is what CVRT is actually pointing to. CVRT. So all this is saying char and UNAT and the dot is we're basically saying how do we interpret this memory that's stored in here right now. So 1, 2, 3, for blah blah blah, then this goes on for 50 bytes, right? So when we interpret this as a character array, we can use something like string copy, because string copy takes in a pointer to a string, and we say, okay, cvrt.string, you're going to interpret this as a character array. So string copy says, okay, this is a character array, great, I'm going to copy in hello world to this, so it copies h e l l blah 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 for the rest of it, right? But then this is still in memory, and now down here I'm getting string length. It's again interpreting cvrt.string. So now it's interpreting this memory again as a string. But now down here, when I do cvrt.data and we're accessing an element in here, because I'm accessing it through .data, now it's interpreting this memory instead of an array of characters, it's an array of UN8 underscore T's. So now when it looks at this, it doesn't see the letter H, it sees the ASCII character of whatever H is actually represented as and stored as, and it says, okay, this is a UN8T, so I'm going to treat this as an integer, and now I can print out H as an integer, which, as we can actually see, that's what's being printed out here, 72, 101, 108, 108, 1. So yes, characters behind the scenes are actually numbers, and I could have done the same exact thing here if I did char and then printed, not char, if I did str sub I and then printed these out as characters, but I wanted to show the actual conversion aspect of this. So this is actually printing out hello world, but if I did this as D and access through the string, it would be doing the same thing, because we're basically saying, all right, interpret characters as numeric data types, but it's not as fun as showing it off like this. I think a better example is to do something where effectively we would have UN8 underscore T data and then have an int in here as well. So if I do, here's a good example, uint underscore 32T and UNAT, and I'm going to have 4 UNATs. So let's actually take a look at what's going on in this case. And this is where you actually really start to see unions shine and make a lot of sense once you're working with conversions between multiple types. So as you know, a integer is a 32-bit my int, and this is going to be my bytes. As we know, an integer is a 32-bit data type, right? So I'm going to have, and I'm going to call this bytes, int bytes, and I'll do a capital I on this guy. Int bytes, and I'll call it CVRT again. Sure, why not? Effectively, int bytes is going to let us access the individual bytes of the int as a converted thing here. So if we do CVRT dot my int, and now I have this equal some big int. So again, ints are 32 bits. We can do something fancy. So why don't I do a hex number 0xFF. Each of these f's is going to be, so each of these is 1 byte, so FF. So this is the integer containing all ones, right? So this is 32 bits of just ones that we're setting here effectively. And they're yelling at me because I don't have a semicolon there. But effectively, now what we can do is we can interpret this as an array of bytes instead. So if I now instead go from 0 to 4 here, and I print out the individual bytes, so I can say something like my bytes here. And now we can access the individual bytes of the character, and we can see that it prints out 255 every single time. If I do %x here, I think this, yeah, so %x prints out an integer as a hexadecimal number. So we can see it literally printing out each individual byte of our integer now, because effectively we're storing this in the same memory that we're storing my bytes in, and we're just interpreting it differently. So an integer can be interpreted as an array of 4 bytes effectively. And that's what we're doing with this union. We're saying, okay, we can store an integer in this piece of memory, but we can also interpret that same chunk of memory as a list of 4 bytes. So an example here would be, let's actually get out, and so we can actually see if we change individual pieces of this, we're going to see that it actually changes what's being stored in memory here. And because this is being stored in, I'm assuming this is, I'm not sure if this is big endian or little endian. You see that when we change the first byte here, we're actually changing the last byte that's being stored in our array. So this is actually endian dependent. So if I make this guy FE, we're going to see that the first guy up here becomes FE, blah, 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 blah. So let me actually pull this up in MS Paint, and we're going to diagram this out just so we understand exactly what's going on. So let me do file new, don't save. And so effectively what's going on here is, again, we're in the stack frame of man. We are, when we declare this union of int bytes, it stores the maximum type. This is the same though. So effectively we're storing 4 bytes right here. So we are storing 4 bytes. So 1, 2, 3, 4, right? So this is CVRT. CVRT. This is the structure of CVRT in memory. Now, when I say, okay, we're going to interpret CVRT as an integer is 4 bytes wide, right? So it interprets this entire 4 bytes wide thing as an integer. So I'm able to now say, okay, this equals something of 32 bits. And because we are, I again don't know if this is big endian or little endian, but effectively the way that it's doing this is it's saying, okay, we're going to start off by storing FA right here in this last thing. Now we're going to store FF in right here, FF, and then FF again, and FE. And this is going to be some huge integer, right? And again, this is hexadecimal numbers, so these are all just some 0 to 255 ranging thing. But now in this loop right here, we say, okay, well now we want to interpret this integer as an array of bytes. So now it says, okay, we can interpret this memory as an array of bytes. We're just going to interpret each of these as their own individual byte. So now, instead of being an integer, this is an array of 4 different bytes, and we print out each of these individual bytes, and it prints out FE, FF, FF, FA. And again, the reason that this prints out backwards is it's endian dependent. So effectively, it's saying, okay, we're not going to effectively it's going to be storing each byte of the integer backwards is what's going to be happening here. And this can actually screw you up significantly if you're trying to do stuff like this, but I've gotten past a few issues with this when I've used this stuff for conversions before. Okay, so what's the next thing that we can do with this? There's a lot of fun stuff we can do with unions. Another example might be, what if we have a long stored in here? So let's actually put a long, so instead of a long, let's actually take a look at some fixed 64-bit, right? So 64 underscore t, and this is going to be my long in here. So the question now becomes, well, what happens if we start interpreting longs as ints, blah, blah, blah? This is actually going to be pretty straightforward. So instead of setting something to equal to my int, I'm going to have this equal to my long. And now we're going to try interpreting it as an int and see what happens. So I'm going to do my long, and again, because all I have to do now to make this a long is double the number of things we store here. And now I'm going to try interpreting this as my int and see what happens, because obviously a long is bigger than an int. So what happens if we have sizes of unequal types? What if they're not all equal to each other? And what we're going to see is, I'm actually going to change this and lower everything down by 1. So why don't I have this be, it has to be something that's not equivalent to the other thing. So I'm going to have it be FAA. Okay. So what we're actually going to see is that when I do this conversion and I interpret, oh, so the converting to my long is actually, I want to convert to my int and see what it prints out. And we're actually going to see it's not going to change, because x is actually only supposed to print an integer. It's not equipped to handle a long. But if I print this out as a long, %l long, I actually have to go look at printf. Give me printf. What's print long? Signed decimal integer, blah, 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 blah. Is there nothing to print longs that they don't give us a means of printing longs? Unsigned decimal, blah, blah, blah. I guess they don't. I guess the highest thing you're allowed to print is... Really? This is shocking to me. Oh, wait, here we go. Length. Specifiers. I don't want to print a pointer here. I just want to print... H is for short int, blah, blah, blah. LL. What? I can't print L, but we're interpreting it as the long. L \n. My long. Why is this not printing the number? This is very strange, because this is sublength modifier specifies the length. Do I have to do like DL? So it would be percent, so LD for long decimal. Yes, okay, there we go. It's a modifier, not the actual thing itself. So %LD stands for long integer. I guess LI works as well. But effectively, oh, could I do long X for long hexadecimal? Yeah, okay, so basically, here we're printing out the number that we put in here. This is the entire number in here, right? But we don't want to interpret it as a long. We want to see what happens when we actually are printing it out as an int. So I'm now going to print out... We're basically trying to interpret whatever's being stored in here as an int. And what we see is that it's actually only getting the final half of it, which is exactly what we would expect when we would be interpreting it like this. Whereas now, if we actually print it out as a... excuse me. If we actually print this out byte-wise, and now we try printing out the individual bytes of what's being stored in here, we have 4 bytes stored. We can basically interpret this as 4 bytes. And now we say my bytes, and again, it is getting those final 4 characters in here. So FE, FA, AA, and FA again are these final 4 things. But illegally, we could go over here and print out the rest of the number as well. But keep in mind that we're promising here that we're only storing 4 bytes, and this is a blatant violation of that. But C doesn't actually care. They're not even yelling at us that this is a warning. We're absolutely going over, but we know that it's being stored there. So let's actually take a look at what's going on here and why this works. And okay, so union in bytes. This is the longer version of what we just did. New, don't save. Effectively, what's going on is now we have different sizes of things in here. So what's happening is I say, okay, I'm going to declare CVRT here, and when we store CVRT in memory, we're going to be allocating 8 bytes for it, because it's always, when you allocate a union, it always allocates the size of its largest element. And this is the core takeaway here. And this, I believe this was a question on the LinkedIn skill assessment when we took a look at it, is what how many bytes does this union allocate? And the answer is it's always the bytes of the largest size of what's in the union member. So this allocates 64 bits, which is 8 bytes, right? So we're going to be allocating 8 bytes for ourselves. And let's see. So I'm going to split this in half. Then I'm going to split these guys in half. Then I'm going to split those halves in half. And this is actually not a very, is this 8? 1, 2, 3, 4, 5, 6, 7, 8. Beautiful. Okay, so CVRT is storing 4 things right here. And because we're telling it to store the long, and keep in mind, because of ediness, this stores the bytes in reverse. So it's FE, FA, then what's after FA? AA, FA again, FE, FF, FF, FA. Okay, so now what we're saying to do is, hey, can we interpret this as an integer? And when we try and interpret this space as an integer, we see that it's too long. So all it's going to do is try and interpret these first 4 bytes as an integer. So it's going to read this out and say, oh, yeah, yeah, we can interpret this as an integer. We're interpreting this part of this, the first 4 bytes, as an integer. So that's why when we actually convert it to an integer and print it out, we see that it only prints out the second half of this because it's only interpreting the first part of it, and there's all this leftover space. Whereas when we say, can we interpret this as an array of 4 bytes, it says, oh yeah, absolutely, we can interpret this as an array of 4 bytes. We're just getting, the pointer to this location right here. And that's what out my bytes actually is the pointer to the first location. But that's why we're allowed to illegally violate this and go over, is because if we keep trying to get bytes beyond this pointer to the first 4 bytes, you see that we actually are just going over into the memory that's been allocated for the second part of this long. Which is why, yeah, we can violate this, but we shouldn't. That's would normally be out of bounds if we were doing this in Java, and they actually kept track of the length of these arrays. Anyway, so this is the main application that I've seen for unions, but you can do some weird, funky stuff with unions as well. One thing that I've seen is structs. Structs, you can have unions. So if you don't know how structs work, structs are kind of like the opposite of unions, where if I declare struct s, and you know what, let's have struct human, and human is going to have, this is actually a good example. We can have human have, no, you know what? I have an even better example. I'm going to have a struct that contains, it's going to be a 2-dimensional vector, right? Or maybe I'll have it be a pair of coordinates. So I'll have this struct be called chords, and I'll have an int x coordinate and an int y coordinate. So think about how else we could represent these, though. So I could say struct chords and have a structure of coordinates in here, or I could interpret coordinates as an array of 2 integers. So I could have int, so struct chords, or I could have int array of 2 integers, basically. So effectively what this is going to let us do, and now I have to get rid of all of this, is I can have something like this, where I can say, okay, I'm going to create a union, and this will be chord union. That is not how you spell union. UIUNION. Chord union. Union chord union equals, and I can do, I'll just declare it as C union. And now I can do C union dot ARR equals 10 and 20 as an array here, basically. And now, if we actually want to look at this as a struct, I can do, no. Union dot chords dot x, and if I return this, we should actually see that this is going to return the first coordinate. And what are they yelling at me for? Union chord union. Oh, because they want this at the end here. All right. What do we want here? Expected an expression before the opening token. Oh, are they mad at me for having this be? I should be able to declare an array like this. What are they mad at me about? This is an int array of 2 ints. What's the issue here? Expected an expression before the opening bracket. I'm perplexed at why this isn't legal, considering you can declare structs like this. But so be it. I'll just say int array 0 equals 10, and we're going to set the second member of our array equal to, I somehow did the character thing here, 20. And now we should see that we can interpret this array as a struct and now access it through the struct. So effectively, we're saying, okay, C union, the array has 10, 20 in it. The struct also has 10, 20 in it. So let's actually do the map of this one, because this is a fun one to actually take a look at. All right. These are all pretty fun to take a look at, but okay. First things first, we are allocating memory for the C union in the space. The largest thing here is, well, chords and the array are the exact same size. The struct of chords takes up 2 ints, and the chord union either represents this thing right here, which is 2 ints, and this is an array of 2 ints, so they're the exact same size. So basically, we're allocating 64 bits, and both of these are going to be integers, right? So this is 32 bits, this is 32 bits. And basically what we're saying here is, in one case, we're interpreting this memory here for the union as an array of 2 integers. And in the other case, we're interpreting this entire block right here as a struct, chords, and then the first part of this struct is X, and the second part of this struct is Y. So effectively, this line right here says, okay, we're interpreting this memory location right here as an array, and we're setting the first element of this array equal to 10. And now in the second case, we're setting the second element of this array equal to 20. But now we're saying, well, let's interpret this entire block as a struct and then access the memory with .x, which gives us the first element of the struct, whereas this y is the second element. So if we did y, we would be able to access the second element of the struct, which is 20. So now if I do chords.y, we get 20. Yeah, program return 20. Huzzah. All right. So effectively, that's unions in a nutshell. Pretty straightforward. So any questions about unions? If there's one key takeaway from unions tonight, the takeaway should be that a union allocates the amount of the maximum member. So the union is going to allocate the largest thing that you're trying to allocate here for in the union, whereas a struct allocates for every single one of its members. So structs allocate an int for x and an int for y. The union only allocates enough memory for its largest member and then puts everything else into that memory that it's allocated, right, for its largest member. Um, we really don't have any practical use cases for unions in modern stuff besides weird stuff like this, where you're converting between. This would be really good if you had like a vector or something, right? So like you could access the vector through its array or through its actual name for an element, especially if you're doing larger things like in x, y, z as your third coordinate, and then you have this b of 3 instead of 2, right? Or if you have a list where each element in that list actually has some name to it that you want to access, and you want to use a union for that, you could do more fancy stuff like this. But overall, the main purpose of unions is for embedded systems where they have very, very, very little memory, and they want to be able to reuse memory for different types. And we haven't really done an example of that, and I can't really even think up a good example of that because we're just never using it because our programs have so much memory. But if you're into embedded systems, you'll probably be using unions all the time. Anyway, all right, that's unions. Now I have to think up. That's really all I wanted to talk about today, so I guess this is a fast one. I don't actually have a homework for tonight yet, but I had a good idea for a homework that involves Vargs. So I should probably talk about Vargs. I don't think I've talked about Vargs yet. So are we aware of how the function printf works? So I'm gonna have main. I don't know why I keep deleting main. But effectively, the function printf is a very fun function because we can do stuff like this, hello world, where we just print out hello world. But we can also do strange stuff where all of a sudden now we can see that this function can take multiple parameters. So I can take in hello world, I can have it take 10, I can now put in 20, 30, 40, 50. And hello world never breaks, no matter how many things I'm passing into it, no matter how many different types I'm passing into this. I can pass in a type of a hello, and this never yells at me or does. Okay, it is yelling. Well, it's yelling at me because of the comma operator. But if I do weird stuff like this, I can pass in a char. I can keep going here and keep passing in things indefinitely, right? Um, Basically, long story short, this is very strange to us because if we actually I know Dan Yi doesn't like it when I go over the assembly, but I'm going over the assembly. If we
I
actually
don't
take a
like it because I
look,
don't understand it.
well, we don't actually go. I don't think we've ever actually gone over anything that requires you to know the assembly rather than subtracting from the stack. Honestly, I don't know why 404 doesn't have you implement a stack, which is like honestly terrible. How are we? It's hard to even talk about how programs work, especially C programs, when we're going over stuff and it's like people don't know what the stack is, what the memory is. It's like this is like what you're supposed to learn in 333, and now you don't even learn this in 333. You just have like a gentle introduction to C in 333, and then in 404 you implement an assembler, but it's not. You don't implement an assembler. You implement a VM, but it's not a stack based VM, right? You guys don't actually do anything stack based, which is like the next step up from what 404 does, and it makes me so sad because you don't actually get to learn how any of this stuff works behind the scenes. Um. Anyway, what I wanted to say was it should be come off as strange. I actually can't show it in the assembly. We're actually going to go jump into the stdio.h source header here because that is what is going to have what we want. Okay, so I'm gonna control click on stdio.h and see if you can guess what the function signature is for stdio.h, because obviously every function needs some signature, right? That says what types of parameters it expects and what it's going to return. So we have to actually think about now what is printf, and there's a gazillion printfs. Dear God, this isn't what I signed up for. Just give me the main printf header. Oh my god, they're gonna have this be comic. Okay, here we go. This is what I wanted. Okay, so effectively right here is our printf function. And we're gonna see that there's something very strange here. We see that the signature is int printf const char pointer to the format, and then we see there's a dot 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 right here. So this is what should be giving you a tip off that this is not a normal function that we're taking a look at right here. This is something very strange that we have not encountered yet. So this is known as Varg, stands for variable arguments, which basically means that you can take huge list of arguments, an infinitely long list of arguments as an array, but then you have to actually parse this array. So let me actually go and we're gonna write a Varg function ourselves right here that takes a variable number of things and then it's doing the thing again. Hang on. I just have to make that bigger and then it stops doing the thing. Okay, so we're gonna write our own Vargs function. What do I want to do with a Vargs function is the good question here. You can do a lot with Vargs functions because you're able to take infinite parameters effectively. I'm going to make a function that sums up whatever you pass it in, not as an array, but as Vargs. So I'm going to have it be an int, and I'm going to call it sum, and it is going to sum up a list of infinite numbers that you pass into it. So effectively, oh, they actually require that I pass in something here, right? Because effectively, so this will be parameter the first thing. So it's going to require that you pass at least one int into it. Okay. Um, I don't know why I called that one. I want this to be called I. There we go. Okay. So effectively, what I want here is a function that takes in at least one integer I and then takes in some variable number of parameters infinitely. And then these are all going to be ints as well, and it's going to sum them all up. So effectively, the way that this works is we're going to actually have go to vargs in C. And they're going to give us, I don't want examples, I want Vardic functions. Okay, so they call them Vardic functions. Effectively, we need this function stdarg.h. It's a library that actually lets us write functions that use vargs. And what's going to happen here is we're going to get access to something called va start, va arg, va copy, and va end. And effectively what these are is va start is going to be a function that I believe is going to let us actually access the vargs. So there's actually a good example in here where they actually are using args in here. Um, they want to give me an example right here. Yes. Okay. So let me grab this, and we are going to actually. I have to X out of all of this fancy smanchy stuff that we're doing. Okay. Goodbye, printf. Goodbye. First things first is probably to talk about VA list, honestly, because I think VA list is going to be so it's an object type that is suitable for holding information. Yeah. For VA start, VA copy, VA end, and VA list. So you can literally think of this as like the array of the vargs that you're passing in. And then VA start is actually going to let us get, I believe it's going to be a pointer to our first arg. I don't know why they're passing an FRMT to this. So the parameters into VA start is going to, first of all, be the VA list that you're going to be editing. And then param n is going to be named parameter preceding the first variable parameter. So what is the point of that? Oh, it's because they need to locate. Okay, okay, I see how they do this. Don't worry about the fact that you have to pass in this first parameter. That's for technical reasons. I'm going to hashtag include this here, scdr.h. Now we're going to have va underscore list my args. Then we are going to do va underscore start. And then we have to pass in my args, and we have to pass in the parameter that precedes my args, which in this case is going to be I. Now, I believe we should be able to actually use va arg to get the next argument from args. So now every time we call va arg, which is this function right here, it is going to access the next thing. And I don't really understand how it does this fancy type stuff right here where they literally have this just defined as t, but they're not forcing me to actually do this. They're doing some kind of like magical stuff behind the scenes that actually lets you get this. So, oh, you have to pass in the type yourself. Okay, you have to pass in the type yourself, which means varg is actually going to be, this is actually a macro then. So if I hover, okay, they're using their special args here for GCC, which we're not actually going to use. We're going to use the standard way of doing it. But effectively, why don't I just do a demo real quick that says, okay, the next argument is going to be an int, and I'm going to set int, sure, I'll call it b to the next arg, and I'm just going to return I plus b right now and demonstrate basically that we're able to use this function to add I plus b. And what are they mad about? It's not called args, it's called my args in this case, right? Compiles, good. So all I want to do is I'm going to return sum of 1 and 2, and this should return 3. Yeah, very exactly what we want, right? So basically what we're doing here is we have a function that takes an I and then a variable number of parameters. And first things first, this args represents the list that's storing the args. Va start basically lets us know where the args start, and we have to pass in the parameter that precedes the args. Then we use va arg with the type that we're expecting for all of our args, and it is going to spit it out. I'm sure this is actually hashtag defined somewhere because you can't actually pass types. This is completely illegal. This isn't actually a function. It's not like we're actually passing a type into a function here. It's a defined macro that's been defined to take a type after some argument list, right? And that's expanding to some expression in our header file. But we don't really care about this. What we really care about here is that we are now allowed to take an infinite number of parameters here for whatever we want. So what I can actually do here is I can do something even more fancy and say, so I need to actually get the number of args, and there is a way to get the number of args. I just completely forget how to actually do it. Let's see, where is my means of getting the number of args? Blah, blah, blah. Ready, int by itself. I know that there's a way to get the number of args in here. Blah, blah, blah. Additional and automatic argument conversions, but I don't really want automatic argument conversions. I just want to get the end's traversal of the Vardic function arguments. Yes, but how do I get the number? C get Vardic get num of Vardic arguments. I know there's a way to do this. I just haven't looked at it in ages. You can't. What? How does printf handle this? You have to manage the caller to indicate the number. Oh, that's how they do it. It's because printf. Okay. So in C++, you're actually able to do this much. They have a much better Vardic system than in C, which is what I was thinking of doing here. But long story short, the way that they want you to do this is there's no possible way for you to get the number of Vardic arguments. So they want the first thing you pass in to actually be the number of Vardic things. So now you can pass in an infinite amount, but you don't actually know what it is. So you have to specify that yourself. But I could do something. So I could say num args here. And effectively what this is saying here is we can do something along the lines of a for loop that goes up to for int I equals 0 while I is less than num args. We're going to have some sum int sum equals 0. And we're just going to do sum plus equals and get the varg from the argument list. And we're going to end this with va end, which tells it to stop parsing. What is it doing? Va underscore end, and we pass in my args again. Okay, so now I should be able to sum up as much as I want if I can actually get this to work. What are they wanting about? Int I, oh, I'm using I twice here. I want to pass in num args here. There we go. What do they want now? Expected a semicolon before a thing. I forgot the I++ in my for loop. How clumsy. Now they're whining about I plus B because, yes, we want to return sum, not I plus B. Okay, beautiful. So now, as long as I pass in the number of integers I'm working with beforehand, I can sum up this many integers using this function. So this is going to sum up to... So 5, so it's doing 1 plus 2 plus 4 plus 5 plus 4, but the only caveat is I have to specify how many things I want beforehand. So you're probably wondering how printf handles this, and the way that printf is handling this is when you do that format at the beginning of printf for frmt, and you basically pass this format string that says blah 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 %d %f for whatever you're printing out, it's parsing this to figure out how many vargs it's actually going to need from you to interpret. So yes, you can pass in infinite things here, but it doesn't actually matter because they're only going to be trying to parse for this many of them, right? What if you don't give it enough arguments? Yeah, it's going to be wonky. Um, Long story short, calling convention in C++, in not C++, in C is going to make this be very wonky if I don't do enough arguments. Because now, let's think about what's happening for a second here. Long story short, the way that this works under the hood in the assembly, which again, I know we don't like talking about the assembly, but it'll be funny to take a look at what's actually going on in the assembly. What's actually going to happen here is VA list is going to be a big object here, and we're saying to interpret up into the so long story short, these args are going to be stored in the memory somewhere because when you pass the parameter, it's actually stored within the call stack frame, and it's going to start interpreting random memory as a parameter here on the 5th argument because we're telling it we're looking for 5 arguments. And because of that, VA arg here is actually going to dip into some of our own memory, probably the first byte of our 32 bytes of VA, or 32 bits of my args, which is some object that's storing some information, is going to be interpreted as an integer here, is what this VA arg is saying, and then added onto the sum. So that's going to be wonky. Yeah, you have to make sure that when you do something like this, now that the number of arguments we pass in is going to be valid. So if we switch this back to 4, though, this should add new, not compiler. What? No, no, give it back. Give it back. Why did you go over to C++? If I reload, come on, give me my. They're not gonna give it back, are they? We're done for. Man, what if I reload the page again? No, they hate me. Okay, okay. I see how it is. So anyway, we're not actually gonna use Vargs tonight. I know I said we're gonna use Vargs for the homework. You're not actually gonna use those Vargs for the homework. We're gonna use the better Vargs for the homework tonight. And the better Varg.
You know how to get back that stuff? Go to load. Use a save and load.
Save and load.
Go to browse local history.
Oh my God, it's actually a thing. Can I like get this back? Hang on. Let's keep trying random ones. Yes, thank you. I didn't even know this was a feature in here, and I've been using this for years. Thank you. All right. Okay. So this works. 1 plus 2 plus 4 plus 5. Okay. So add sums to 12, right? So this is actually really powerful because we can start writing more generic functions if we want. And obviously this is how printf functions and everything. Again, this is very powerful. If you want to do similar functionality, of course, you can pass arrays to things, but it's nowhere near as powerful as being able to literally determine your type of things here as well. So Vargs are very powerful, and Vardic functions, which are what we're looking at. What we're actually going to be interested in working with tonight is Vardic define macros. So we're going to actually go look at C Vardic macros. Not cardiac muscle. Vardic macro. Okay. I actually don't think it's pronounced Vardic. I like to pronounce it Vardic, but I think it's variadic. I like how there's a Wikipedia article on this. I didn't know there was a Wikipedia article on this. Okay. Let's see. I want any of this fancy stuff. Give me CPP reference. The best reference. C Vardic macro, CPP reference. Gonna give me the Vardic macros on here. They are okay. So what we want is vargs and vopt. I don't even remember what vopt does. What is vopt? Content, which is replaced by content if vargs is non-empty and expands to nothing otherwise. Okay, let me just read this really briefly. Of the defined macro with variable number of arguments, additional arguments called variable arguments can be accessed using vargs, which is then replaced with the arguments supplied by the identifier that is supposed to be replaced with the arguments. So if you pass this in, it replaces. So they define f, and then you pass in ABC, and it's going to place what, a comma on the end of these? Yeah, with vopt. Okay. vargs. Right. Okay, so effectively, what we want to be doing is something along these lines. So I'm going to define a Vardic macro here. So you might remember function macros back in the day where we did fun stuff like max AB is defined to be basically the greater of A and D, right? Using an ternary operator, A and B, right? Pretty straightforward. So this, if we actually go take a look in this, and we do the max of 3 and 4, we can get stuff like this, where the program will return 4. What I actually want to do is I'm going to add a new compiler on here, and we're going to put in the -e option, and we're going to see what this expands to. And of course we have all of the libraries that are included in, but we can see that the main function then actually expands all of this out, and we are returning, if 3 is greater than 4, we return 3, otherwise we return 4, which obviously that's going to return 4. Huzzah. Okay. The next thing that we're going to look at is the actual Vardic macros. So the way that this works is we put in a ... here, and then we can use this special keyword vargs to expand out to whatever we're passing in here. So if we're going to do the most basic thing of this. I'm just going to have this be called f, and we are going to have this be f of a, b, c. And we're just going to take a look at what this actually expands out to. this doesn't actually have to compile to anything. All we care about is taking a look to see what it does. So effectively, what we see happening here is that dot 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 and then vargs literally expands out to A, B, and C right here with parentheses or commas in between them. So this lets us pass in a variable number of identifiers into here and then actually expand them out in here. So the reason we would want something like this, at least the reason that I like to have something like this, is what if I want to declare something like an array in here? So I want my f to actually be an array declaration, right? So I'm going to have int. This is a terrible example, but I'm going to have it be called like int. You know what? I'll pass a name in. Why not? Name dot dot dot. So the name of the array, and then have it be unsized and then equals vargs right here. So effectively, this is actually fully legal. I don't know if I told everyone about this on the day that we went over arrays, but effectively, if you leave this empty, it's going to initialize to the size of the default, whatever you're putting in here for the default, which is going to be surrounded in these brackets, and I won't put a semicolon because I'll leave it to the user to semicolon this. But effectively, let's say that I want to have some weird way of declaring an int array with the letter F, and then I'm going to do F and then the name of the array, which I'm going to take this, and I'll have this be int arr, and then our members will be 1, 2, and 3. So basically what this is expanding to is us declaring an int array with 1, 2, and 3 in it, and if we go look down in main, we can see that that's literally what this expands to. So f int array expands to int array of with 1, 2, and 3 in it. And this is us using vargs basically to actually specify what's going to be inside of the array. So this is pretty straightforward. Why might you want to do this? Well, because you might actually want to reuse vargs later on. Say I want an int array, but I also want an int array with some additional properties declared on another line. So I'm going to put a semicolon right here. And now I'm going to go on to the next line to write the rest of this. I'm going to have another array here with a separate name that's been changed. So this is going to be array, and then this is going to be potentially the float version of this array. So I'm going to call it name, and I'm going to concatenate it with underscore float, and I'm going to put the vargs into this. And now if we actually do this, and I'm going to have this be array, and you know what, I'll actually concat this with int as well. And now what's going on here when I declare farr123, this actually declares two arrays for us. We now have access to arr underscore int, which is going to be these three numbers as ints. And we're going to have access to a second array of type float that has these numbers in them. So I'm going to have float int and float. So I can actually do fun stuff like, let me go actually take a look to make sure this declares properly. And yes, it does. As we can see here, it does int arr underscore int 123, and it also declares the float array with 123. And there is a double semicolon here, which doesn't actually matter. Double semicolons don't do anything. Sometimes they'll throw warnings if you're in all mode in the compiler, but we don't really care about that. And in fact, this is actually pretty common when using macros. You'll see a double semicolon, so the empty statement that doesn't do anything. But effectively, what we're doing here is we're abusing the fact that we have Vardic macros now to be able to create multiple arrays with vargs here. So this is creating two arrays. One is a float array, and one, oh, no, it's not. I want this to be type float. There we go. So one is of type float, one is of type int. And just by doing this, we're creating two arrays with the same content, but one is a float array and one is an int array. And now, obviously, we have access to these, and we could do for loops, blah, blah, blah. But that's not what we're trying to show off. I was just trying to demonstrate a practical application of Vardic macros. My personal favorite application of Vardic macros is Enums. Effectively, we want a way of declaring enums and declaring a lookup table for the enum strings. So that's what I was going to have your homework be tonight, is essentially I want a way of declaring an enum. So when I actually declare I'm going to have this be all caps enum, And effectively, I'm going to have the name of the enum, and then this is going to be the contents of the enum. But it's going to declare two things. The first thing that it's going to declare is it's going to actually declare the enum itself. So it's going to be like enum name, and then inside of the enum is actually going to be the vargs. So let me grab my VA args. I actually don't even know what this VA opt does. I've never actually used VA opt. What does VA opt actually do? VA opt equals brackets VA args. I'm trying to figure out what VA opt does because this actually looks kind of useful, and I might want to use this in the future. So here they're using VA opt. Is it like what's put in between the vargs? Equals VA opt. I'm struggling to understand what VA opt actually does here. VA opt content is replaced by content if VA args is non-empty and expands to nothing otherwise. Oh, so this is like an if statement that checks if VA args has any content, and then otherwise it's nothing. Okay, so that's actually kind of lame and not useful at all for our cases. So basically, right here, I'm going to say name and then VA args here, and then I'm also going to want. I'm actually kind of spoiling this entire thing right now. The assignment. I want a lookup table of const char pointers, const char pointer. And again, this is an array of strings effectively that contains the actual names of each individual Varg. And this is actually a very, very fun exercise to do. And I've actually done this in C++ before because I wanted my enums to have a lookup table built in with them when we declared this. So effectively what you're actually going to have to do now is actually use. It's actually I'm debating whether or not this is actually going to be legal. How did I do this in C++? Because we don't actually have access to so I'm sure we're aware of this operator which converts everything to a string, which is exactly what we want. But I actually don't know if it's going to do that. So if I do something like this, what happens if I do enum meme, name my enum meme, why not? I don't know why it's not doing uppercase. Meme, and I'll have ABC. Sure, why not? ABC. All right, give it to me. What do we got? Let's see. Meme, const char, ABC. So this converts all of them to just a string, which I don't want. I want to null terminate all of those, but they're not going to let me do that. How did I do this in C++? I know I did this. I know for a fact that I did this in C++. Let's see. I don't want to use any of their fancy stuff. Okay, yeah. So the operators, when a hashtag appears before vargs, the entire expanded vargs is enclosed in quotes. If the hashtag operator between any two successive identifiers in the replacement list runs parameter replacement on two concatenation, only tokens from a valid token pasted, identifiers. Okay, I don't want to do undef. But how are they screwing with this? I know for a fact that they're doing something here. Let's see. Puts expands to puts. I could have them get rid of the strings, which is what they're doing. All right, you know what? This is actually a bad assignment because we'll be here for like 10 years trying to figure out how to get this to work. Because this here is expanding to this string, fancy string right here. But I wanted something else. Some compilers offer an extension, in which case there's nothing to variable, but removes the comma when the variable arguments are not present. This makes it possible to find macros such as fprintf, blah blah blah. Do I want to even experiment with this? What does this actually do if I do this? No. Okay. They don't actually let me use the double on this compiler, which is a shame, but there should be a way to do this. I've done this before, and now I need to think about how I could actually have this implemented. You could theoretically go. Okay, you know what? We're not actually going to have we're not going to do this as an assignment. I need a different assignment now for the homework, which is sad because this was such a great assignment to have it automatically generate an enum and the enum lookup table. And I've done this before in C++, but all good things must come to an end. I guess in C, it's not going to be as feasible as I wanted it to be. So instead of that, what we're going to do instead is, let's see, I can have it do. No, there's totally a way to do this, but you just look for the end of the string or a comma and define a function as well. But we're going to, let's see, I'm going to look up good assignments for unions and enums. Let's look up a good union assignment. Union questions in C. All right. I don't really want examples. I'd prefer to get union like questions that make people want to use unions. Are there any like good questions? Union exam questions. Questions. C union exam questions. Quizzes and worksheets. C. Okay. Which is probably, I want to have a worksheet. I want like a project. C union projects. Let's see. I honestly like it's so rare that you would have to use a union. Enums are more common, but they're only used in like really big applications, and I don't want to have people writing like big applications. I mean, I could do something like the color thing and have you implement for like more colors, but I ain't really to go over ANSI colors other than like in passing. So it might be kind of annoying to do. Um let's see. I could have a function that takes. Yeah, okay, okay. You know what? I have an idea, at least for the enum example. I can have you take. All right, let me actually go to my document. I don't know. I didn't want to full screen that. I wanted to keep hitting enter until this went down to a new page. And I want to put you on a new page as well. And all right, so for the homework here, I'll put in. Let's see. I want to write a color enum for 16 colors. I want them to be the ANSI colors, basically. So I don't know if you guys ever learned about ANSI colors, ANSI color codes. I love my ANSI color codes. Effectively, what we have here is a means of displaying colors in the terminal. I'm going to use, can I use the arbitrary 64-bit true color? Where is true color? True color, true color. Should I explain the true color ones instead? They might not even offer true color. We might just be better. Yeah, all right. So we're going to do the 16 different FG colors that they offer here. Is this 16? 1, 2, 3, 4, 1, 2, 3, 4. This actually doesn't look like 16. Is this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, yeah, that is 16. All right, so I want an enum that gives you all 16 of the ANSI color codes, which I'm going to link in the homework sheet. And I will share an updated version of this. So color for each of these 16 colors. And what I actually want you to do is try having this isn't that big of a task. I want you to make the matrix thing. You guys know the matrix thing? The matrix GIF. You guys know this famous GIF from the Matrix where they have all of the text in a certain color going down the screen, and some of that text is lighter or darker. I want you guys to do one of these things where you have characters basically scrolling down the screen of various colors. And I want you to specify the color with an enum. And the way that you're actually going to access the color, this is actually extraordinarily easy to do. You're not going to be able to do this in Godbolt. Unfortunately, you're going to have to do this in a real terminal because you're going to have to clear the terminal every single time. I'm going to show you guys some hacks really quickly that you're going to need for the homework assignment tonight. And what I'm going to have you do is I'm going to have you also return all of your functions. I don't want any of your functions to return anything. Anytime you're editing something and returning a return value, I want you to return an enum as an error code for something that could have gone wrong in your function. If something is out of bounds, I want your function to return an enum error code that says this is out of bounds, because this is how all libraries actually work behind the scenes. If we go to the Vulkan reference right now, and I go to the Vulkan reference, we're gonna let's see. I want Vulkan API reference pages. I just want to see the entire thing of what's going on here. Every single function returns VK result. It's always going to return an enum that says this is what we did. And the return is always going to be a pointer. So if like if you have something that you actually want to get out of a function, you have to use a pointer to actually change what you're not change, but effectively the result is going to be stored in some thing that you pass into it, and the return is always going to be the error code. You can see right here another thing, error code. Let's see, and what do we actually want? What does this actually do? Acquire next image. So as you can see, normally if you wrote a C function like this, right? So it's taking a bunch of parameters and it's returning an image, but it's not actually returning the image. It's actually writing to this. It's writing its output to one of its inputs, which is this final pointer right here, whereas the result is actually an error code to check if something went wrong. So I want every single function you write should return an enum for your error code, and anything that goes wrong, return the enum error code. And then I want you to take in an enum for whatever color you want your thing to be. If you want to go super hardcore, do like some fancy rainbow thing where you pass in each of these is like a struct, represented as a struct, each line of characters coming down that's represented, and it'll be glorious. But the other thing that you guys need to learn is how to actually clear the screen. And I'm going to do this in over here because we actually need the ability to talk about what's actually going to be going on here. So what I'm going to do is I have to run this in an external prompt, otherwise this isn't going to work. But what we're going to do is first I'm very briefly going to talk about how colors work in the terminal. Effectively, the ANSI escape code \E lets you start to use colors. Now, there's a lot of different escape codes that do a lot of different things. You might know \A lets you do a beep, and it literally will just beep, makes an audible noise right here. So if you do \A, and I run this program, it's going to start beeping at me. In fact, back in the day when I was first learning C, the funniest shit that we would do in programming class would just be to do a infinite while loop with. uh, this was gonna. Last time I did an infinite loop, it crashed. But you know what? I'll do like printf a, printf a, printf a, printf a. I actually don't think you can hear me because I'm sharing screen, but I mean, we can, sure, why not? Let me gcc hello world dot c, and I'm just going to turn this right into an exe. I don't care about object files. I'm not linking any libraries right now. And now if I actually run this for me, I'm going to hear a bunch of beeps, exe. Oh, I actually didn't hear any beeps. Maybe this terminal can't make any beeps. If I pull this up in a real command terminal, let me do open. I want to open an integrated terminal. I'm going to just type cmd. Oh, they literally, okay. cmd /c cmd. Okay, now I'm just going to cd into this directory from a new terminal. cd here a.exe. Okay, so I got the beep. I heard the beep. I don't know if you guys heard the beep. It makes like the Windows error noise. So every time I run this program, I hear da 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 Windows error noise. But effectively, Um, the funniest thing back on my like Windows 95 computers, you would do yeah, what Brian posted, which is the infinite loop of \A. So printf isn't only for printing things, which some people find very funny, but effectively there's what we care about is this character right here, the ESC character, which is \A. And now we have things called escape sequences, which give us like insane control of the terminal. This is how they used to do like ASCII games and everything. You can do an entire ASCII game, like ASCII Dungeon Crawler, just using escape sequences. You can do some crazy stuff. You can move the cursor around. in your application, you can do basically everything. There's so much stuff you can do with these escape sequences. But the one thing that we care about is we care about this right here, this specific code, ESC bracket 1 something M. And effectively what this does is each of these escape sequences, \E, represents, hey, everything after this print in some color. So I'm going to do hello here. And now everything after this is going to be printed in whatever 31 is. And we can look at this color table here and see that 31 is red, right? So everything after \E bracket 1 colon 31M is going to be printed in red. So if I do hello and now I run this program, cmd, okay, hang on, exit, exit. I don't know how many layers in I am right now. Oh, that was the final one. Okay, if I recompile this, and now I run a.exe, we actually see it prints hello, but now we see my entire terminal is in red. So anything after this, everything I type now is going to be in red. And the reason for this is because to stop it being in red, you have to put another thing at the end. It's kind of like HTML tags. The tag to stop color is \bracket 0M. And now this will actually stop whatever color we're in. I'm going to change this to a different color to show this off. So if I have, what's green? Green is 32. So if I put 32 here, we're going to see that effectively what it does is it's going to print out hello in that, but now any characters after this, so this is after hello, are going to be in not a color because we've turned the color off with this tag effectively. So I honestly like to think of these as HTML tags, where it's like this is the tag that says I'm red, and then this is the tag that says I'm no longer whatever color I put in. That ends the tag. So if I do gcc hello world.exe and now I say a.exe, we see it prints out hello in green, and then this \ze0m tells it, hey, stop, don't do that anymore. And you might actually be surprised that this actually works for like every programming language almost. In any programming language, if you print out these specific characters, you can turn your terminals different codes different colors. So all of the strings you print out, you can control all of their colors with these special character sequences. Yes, yeah, absolutely. You never learn about this because it's too fun for computer science classes. They don't want you to have any fun in 201 and change the color of your output. Yeah. So this is very, very fun to do. And what I was gonna have no, it's terminal specific. It's not based on the programming language. The terminal is actually what's parsing what's coming out here. And the terminal reads this string and says, oh, okay, I see that you have this code right here. I'm going to interpret this as a specific color. So this is essentially, is that real Tony Comanzo or is that the Brandon Tony Comanzo? That's Brandon. That's Brandon. Tony's not online right now.
No, it's real Tony.
It's not. I know that's Brandon. Okay. Anyway, so that's how you get different colors. So effectively, for the project for tomorrow, and again, you don't actually have to do this by tomorrow, but if you think this would be a fun project to do, I want to see the matrix effect in C by having the characters scroll down the screen. You can select a random character, you can do a set character. I just want the characters to scroll down the screen. I think that's going to be really cool. So the one thing that you're going to need to know other than this is the clear terminal command, which is actually pretty simple. It's I actually don't know if there might actually be an Ascii code to ANSI escape code that clears the terminal. Let's see. Can I get so this is select graphics parameters. There's reset, blah 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 blah. I just like to use the command. There might actually be another way of doing this. Let me know if you find another way of doing this. But what I always used to do this is system. And then you guys might know the command CLR or is it clear in Windows? Yeah. So the clear command clears your terminal. It's much faster over here if I do CLEAR. It clears your terminal. And this is the case while the program is running as well. So if you run system clear, it executes this command basically on the command line behind the scenes and should clear the terminal. So if I do this and then I printf something else, it should clear the terminal and only print out the second thing. So if I do this 32, we should only see the second thing print out here. So if this is going to work properly, it should print this out and then immediately clear the screen and then only print out meme. So if I'm compiling this, GCC hello world. Okay, so because I'm on Windows, system is going to be included in my version of Windows.h. And Linux also has system included somewhere in it. I just don't know where. And I think the Linux clear screen command is something else. I think it's CLR. I mean, we can Google this for anyone who's going to be programming this on Linux. Linux CLR. Linux clear terminal is what I want. Clear terminal. I know there's a command for it. You can't lie to me. What is it? Oh, is it just clear? Okay, it's just clear. Okay. And how do I get system in Linux? System in C. Yeah, okay. So in Linux, system is included in stdlib.h. I actually wonder if it's included in stdlib.h for me as well. I probably don't actually have to include windows.h. Like, can I just do this? Oh, I guess I can. Yes, nice. So the system function in window or in not Windows, but in C basically lets you pass a command to the command line from your C program. So effectively, let's actually now see if this works. So if I run a.exe, we see that it clears the screen. So basically, this is printed out hello after hello, but it's clearing the screen first. So to do your matrix effect, what you're going to have to do is do a big infinite while loop. And at the beginning of the while loop, you're going to clear the previous frame. And if you want this to run at like 60 FPS, you're also going to put a sleep in there. So it stops before clearing the screen again. So I think there's a sleep command there's definitely a sleep command in Windows. C sleep. And there's also definitely a C function in Linux that lets you sleep. So in Linux, I think sleep is in unistd.h, whereas in C sleep in Windows, it's going to be in windows.h, I believe. Yeah, include windows.h, and then you do capital sleep, and then the milliseconds. Whereas in Linux, you include unistd, which is the Unix standard, and there's a sleep function in the Unix standard as well. So if I want to pause my program before this clear happens, I can, at least in Windows, hashtag include. And remember, if you're on WSL, you're not using windows.h, you're using the Linux version. So if I do include windows.h, and now I do sleep, and I sleep for 1 second, which is 1,000 milliseconds. Effectively, what's going to happen here is we're going to see this text, and then it's going to clear the screen and then print meme. So if I do something like this, a.e, nope, that's not what I want. I want to compile first. And it's going to take a second because windows.h is huge. We see that it prints that out, then it clears the screen, and then prints meme. So this is basically everything that you need to do to do the matrix effect. Obviously, this is going to be more pronounced if you're actually in a real terminal window. I don't recommend developing in the VS Code terminal. I recommend developing in your real system terminal. So if I cd into this right here, and now I run a.exe, we're going to see that this effect is much more pronounced. Oh, and they actually color that for me. Why didn't they color that for me? That's legal. There's legal coloring in here. Are they really not going to color my output in here in a Windows terminal? That's upsetting. So if I run this, wow, do they not color code in Windows terminals? This is going to be an issue for me. Windows color code escapes. Using ANSI escape codes in the Windows terminal. No, they do. ANSI codes by echoing the foreground color, background color. That's the printf. Yes, 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 yes. It's not cleared at that point though. It should let me. Okay, so they're doing this fun stuff. Echo off represents the escape character. That's not what I'm getting. Recognize the ANSI v blah 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 blah. Yeah, so this is what I'm getting. This guy is getting the other thing. Update for the latest Windows 10. Read closely. Okay, so they just changed this, it looks like. Blah, blah, blah. How long ago was this? 2013. Oh, edited in 2020. Okay, so this actually changed recently. Blah blah blah. You have to enable something. ANSI.sys does not apply Windows NT. Do not have nice ANSI support. Really? You're telling me that they disabled this in the latest version of Windows? Really? 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 This is so depressing. You can enable virtual terminal processing to enable this. Starting from Windows 10, you can do this fancy thing. Simple cursor, blah blah blah. What if I literally just I don't have high hopes for this, but it's possible. Would PowerShell work? So I'm sure they have their Windows has probably has its own thing. Let's try PowerShell. Why not? Let me go to PowerShell. Windows PowerShell. PowerShell definitely has colors. I just don't know if it's gonna use ANSI color codes. Well, this is certainly taking a while to boot up. All right, cd into this directory. Whoops, that's okay. Good, we're in here now. And if I run a.exe, a.exe is not recognized as the name of a. It's literally a thing in here. A.exe, right there. Do I have to run // in PowerShell to start the exe? A.exe. Nope. All right, does not work. Clears it. Still does the thing, but unfortunately does not actually accept my ANSI colors. Okay, so I'm going to attempt to hack the hell out of this right now because they're going to try and ruin. They're going to ruin my Matrix project at this rate. Can't have this. Let's see. So they want me to take a look at this, blah, 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 and I don't want to do any of this fancy stuff. The following terminal sequences are interpreted by the console host when written to the output screen. If enable virtual terminal processing is set on, let's see, is this a flag? Get console mode, set console mode. Win API, set console mode. I have to get the console handle. Oh, this is gonna be a huge pain in the butt to have them work this out. I'm not gonna brick my computer this time. Not this time. I hope. Let's see. So what if I do a bash shell? So I have bash on here. Oh, of course they don't actually want me to have bash on here. Where bash? I do have bash on here. I know there's another instance of bash. You can't lie to me. I don't want the system32 bash. I want this bash. So if I use my msys bash, and now I cd to let us cd. I wonder if now this is the right terminal. So if I cd to where am I? C users James. I'm gonna cd to C users James desktop repos blah 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 blah. cd users James. Oh, I need the C there. Hang on. They're mad because the it's in the other direction. So they want me to actually do forward slashes. So cdc users James desktop IEEE. No, it's in repos. IEEE winter series bash. Yes, that's why I want a cd and I type cd. Like that is a directory. Yes, yes, it is a directory. Thank you. Okay, so now if I run a.exe in here, do we actually get my colors? A.exe. Okay, it's bash, so I have to do /a.exe. No, really, they still don't let me do colors in here. This is the most depressing thing I've ever seen. What if I do it in a special MSys terminal? This is tragic. MSys. I'm getting destroyed, man. Right, I'm pulling up a special terminal, which may or may not actually be a Windows terminal. I'm unsure if this is a Windows terminal or not. So I'm gonna cd c/users jams desktop repos IEEE winter series, and now I'm going to try to do /a.exe. Yes! Alright, there we go. Alright, just don't use your Windows terminal. Use your special thing instead. Use a special terminal. This is yeah, okay. Hello. Wait, but it didn't clear screen. Oh, because it's not Windows anymore. Okay, yeah, because this is actually right. Okay, long story short, this is being interpreted as like a Linux terminal. You should view this as a Linux terminal. All right, so you have to use a Linux terminal in order to get these colors to work. You're welcome. Problem solved. If you're on Windows, just use your WSL terminal, and instead of including Windows.h, yeah. You have to use unistd instead now. So unistd, and I'm going to test this again, but I'm not going to compile to an exe. I'm going to compile it just to a.exe. So I'm actually going to output this in Linux format. So I'm going to do a. This actually might not work. If I had WSL on here, I would actually. I didn't cause a blue screen ever. This is a lie. They've lied to me. This is a lie. Don't trust them. Anyway, long story short, attempt to do a matrix program. That's your homework. No homework for unions because you'll never use a union. All you have to remember about unions is when they ask you what size the union is, it's the size of its largest member. Huzzah. All right. Well, that's everything. It's 10:03. We're over. All right.